All right, let's take a look at how to deal with downward projectiles. And what makes this different than what we've done so far is just one fundamental change, okay? And that change is, let's picture you're standing up on a roof and you're throwing a rock off this roof. Now, everything we've done up till now has been something leaving horizontally or projectile leaving vertically where we throw it up and then it comes back down. What if you're standing up here and you're just throwing a rock down into the parking lot? It's going to take off with a downward trajectory, and then eventually it sort of looks like a parabola at the end because gravity starts to take effect as soon as it leaves your hand. So what we're going to have is different is we're going to end up with a downward component of velocity right from the beginning. Okay, so the mechanics won't really change. We just have to remember that fundamental difference that it's not starting with an upward trajectory, it's starting with a downward. Now let's take a look at some numbers I just made up here. Let's say you throw a rock off a building at 50 degrees compared to the horizontal. Okay, so like a 50-degree angle downward. All right, and we're going to throw it with an initial velocity of 12 meters per second. That's the resultant velocity, the angled velocity. The first thing we're going to do, as we've always done, is we're going to take a look at what those components are, the vertical and horizontal. I got the vertical in blue and the horizontal in red. And once we get those, we're pretty much going to ignore the original 12 meters per second because all we're using is the components in our analysis. So if I set this up, the vertical is going to come from sine. It's going to be 12 times the sine of 50 degrees. Okay, when I plug that in, I've got all these calculations done already. Okay, when I plug that in, I get a vertical component of 9.2 meters per second. Doing the same thing with the horizontal, the cosine of 50 times 12, which was my hypotenuse, I'm going to get a value of, let's see here, we got 7.7. Okay, so I've got my horizontal is 7.7. Now keep in mind, I'm throwing it downward, but it is going to continue moving at 7.7 meters per second this direction, constant. There's nothing to slow that down except for air resistance, and right now we're going to assume air resistance is negligible. So without any air resistance, there's nothing to slow it down or speed it up. It stays the same constant speed of 7.7 horizontally all the time. Okay, gravity does not affect that. It's independent. What gravity does affect is the vertical. It's going to start with an initial velocity of 9.2 meters per second, and then it's going to continue to speed up and speed up and speed up until it hits the ground because gravity is going to accelerate. Okay, now remember we've talked about a lot of different ways to set this up with negatives and positives. You just have to be consistent. We're going to go back to comparing this to some of the previous problems we've done, and I'm just going to list out the things that I know. Okay, I know my initial velocity, vertical, is 9.2 meters per second. I'm basically going to ignore that right now. I'm not going to pay attention to it because it doesn't matter in my analysis. Okay, my final velocity, I don't know. Let's see, acceleration. Okay, in this case, I know that as soon as it leaves my hand, gravity is going to be speeding it up. The rock isn't going up and then back down, it's going to be going down the whole time. So it's speeding up the whole time. So I'm going to make this a positive 9.8 meters per second squared because it's speeding up. The time it takes to get to the bottom, I don't know that. Okay, it's another unknown, but I do know I'm standing on top of a 20-meter tall elevated platform, a building or something. So my displacement is 20 meters, okay? And I could think of that as the final displacement. I can also think of that as the initial displacement. It depends on how I want to set this up, okay? So when I look at my formulas that I have to work with, I got two of these unknowns, and they happen to go with two of the easier formulas that I usually are my go-to equations. So I'm going to start with the one that a lot of people avoid. X final equals X initial velocity times time, plus 1/2 AT squared. Okay, now if I look at this and I think that my original starting position was 20 meters, then this right here would end up being 0. However, that means it's also going in a negative direction. So if I want to turn this into all positive numbers, what I'm going to do is I'm just going to think of my total change in displacement as 20 meters. Okay, which means I can kind of pick this however I choose. I like to deal with a lot of positive numbers if possible. So I'm just going to keep it consistent that way. I'm going to say that we're starting with an initial displacement of 0, and we're going to end up traveling a total of 20 meters at the end. So 20 equals 0. Okay, now my initial velocity right here, my initial velocity I have, that's my initial velocity right here is 9.2. Now usually that's 0. In this case, in a lot of the situations we dealt with horizontally, but in this case it's not. So I'm going to go 9.2 times time. Okay, now I don't know the time. And then I go plus 1/2 positive 9.8 times time squared. Now I wanted to write this out so you could see why we're going to take a different direction, okay? Every once in a while in physics, you kind of get to a spot where you go, this is not working out nice the way I want it to, okay? It's not taking me a good direction. If I want to solve this for t, that's a quadratic equation, okay? It's going to input 2 solutions. I'm not saying it isn't possible to solve, but it's a pain in the neck. And one of those solutions will be realistic and another one won't make any sense. Okay, so when I look at this, I go, I got a t here and a t squared there. This is not something I can factor. I'd have to use the quadratic formula. I'm going to stop and back up. Okay, I'm not going to get rid of this. I'm going to come back to it. Okay, is there another way we could go about this? We also had a formula that said final velocity equals initial velocity, and they were both squared, plus 2ax. If I had started in that spot, what do I have to work with? Do I have an initial velocity? Yeah, I do. Do I have an acceleration? Yes, I do. Do I have a distance that it's going to fall? Yes, I do. This one would have been a lot easier to start from. So occasionally you're just going to get going and you're like, hold on a second. Where I'm at, this is not working out well. I'm going to come back to that. Maybe I use it, maybe I don't. So now, does final velocity help me in this analysis? Well, it kind of depends on what you're looking for. Right now I'm going to try to figure out everything that I can. But sometimes you need it and sometimes you don't. So final velocity squared is going to equal my initial velocity squared, which is 9.2 squared plus 2 times 9.8 times 20 meters. Okay, now I didn't put in the units, but we can compute this out. And when I do this and then I end up taking the square root of both sides, square root of all that stuff, my final velocity in this case comes out to be 21.8 meters per second. Okay, now keep in mind, everything we've written in blue is just the downward components. It's moving downward at 21.8 meters per second when it finally hits the ground, assuming no air resistance. Okay, so I got a final velocity of 21.8. All right. Now, we go back to where we're at. We still would like to know how long it takes for it to get to the bottom. The reason we want to know how long is because time, remember, is our connecting unit. Time is the same for either situation. The rock's in the air for the same amount of time whether you're looking at it vertically or horizontally. It hits the ground at the same instant. So I look at this and go, well, now I could take final velocity, and I look back up here to where I was headed, and like, that doesn't really help me in this one. But I could go to my original formula that I'd used before. Final velocity equals initial velocity plus AT. And I'm going to go, all right, 21.8 equals 9.2 plus 9.8 t. Remember, it's positive 9.8, so it's speeding up. If I solve that for t, it should tell me how long it's in the air. When I solve that, I get t, what do we got here, 1.28 seconds. Okay. So it takes 1.28 seconds to hit that bottom. That seems like a reasonable number. Okay, that's what's nice is 1.28 seconds is the same whether I'm looking at the horizontal components or the vertical. It's in the air for the same amount of time. Now the horizontal piece is actually pretty easy. It's moving a constant speed of 7.7. That's not changing. There's no acceleration. 7.7 meters per second. So I have a speed or velocity. I have a time. If I need the distance, I just do distance equals velocity times time, and I multiply those together, and I get a distance of 9.85 meters. So this will fall 9.85 meters. It will be 9.85 meters from the edge of the building when it hits the ground. Okay, that's pretty much everything there is to figure out. If you're looking at this going, why did you do this? The answer is I didn't have to. But I'm starting to get feedback from a lot of students that they're just kind of headed down wrong paths, and I think it's a good idea when you get to something you go, I can't use that, or I'm stuck. Don't erase it. Don't get rid of it. Leave it there. It might be something you use later on depending on what you're working for. Okay? Maybe it isn't. But just keep trying equations until you finally solve for the pieces that you need that are left over, and eventually you'll have everything figured out. You do all the physics, they'll all tell the same story. If I plug my time in here that it takes to get down to the bottom, I should see it, this stuff equal this, within reason, maybe a little bit of rounding difference. Okay, and there's downward projectiles.